Recording in progress.
It's a real pleasure to welcome Tony Lynas-Gray to the IAC. As you know, Tony had some unexpected health issues in the last few days, but now he's feeling better. He's recovering, and he's very kind in giving the seminar today. I'll just give you a short timeline. Tony's trajectory. So Tony graduated at the University of Bangor in North Wales in 1971. Then he did his PhD at St. Andrews University in 1974. He was also a postdoc at St. Andrews University and then at UCL. And then finally, Tony moved to Oxford in 1988, where he worked as a research assistant for almost 30 years. During his time in Oxford, he was heavily involved in teaching, tutoring students, and now he's a senior honorary research fellow at UCL since 2017, and also is honorary research fellow at the University of Western Cape. A few words about Tony's research. In the early days, Tony worked with Professor Donald Blackwell on the analysis of solar iron abundances and the computing of stellar spectra. He has also studied carbon stars in the near infrared using data from the Carlos Sanchez telescope. That was in the mid-80s, I believe.
It's fine.
And more recently, Tony is working in stellar pulsations. So today, Tony is going to talk about new molecular data for astrophysics, the ExoMol project. So,
thank you very much, Jorge, for that introduction. I need to accept. I apologize for this delay, ladies and gentlemen. They say you never should begin a talk by apologizing.
this one.
He's crazy because I'm not going to use the keyboard.
Showing yet where
Muy bien. ¿Lo cambiar o no? No. Ah. Okay. Okay, so my time here in Tenerife, when I first came to Tenerife in 1983, we had some time on the Carlos Sanchez telescope. It wasn't called the Carlos Sanchez telescope at that time. It was called the infrared flux collector. And Robin Clegg applied for some time for us to observe carbon stars and M giants using the cool grating spectrometer, which was, shall we say, a new infrared instrument at the time. And we could get some useful data for some of the brightest objects in the sky. These are objects of around 0 at K. And so the idea was to get some spectra and do some analysis. And that was for me an introduction to cool stars and molecular data, molecular spectra. And then when I worked briefly on hot stars thereafter. As I mentioned, after some bit of work on the sun. And after that, I came to retirement. And Jonathan Tennyson said to me, well, why don't you join my group at UCL to compute new molecular data? And he'd been running this group at that point for about 7 or 8 years. And it was just a question of really having enough hands to run the computer programs to compute data. So I done some work on the carbon-3 molecule, which I'm going to tell you about. And I'm also going to try and set that into the context of new molecular data for astrophysics in particular. One of the things that was quite noticeable out of the Carlos Sanchez telescope data that was obtained in 1983 is the fact that Carlos Lázaro kept on saying, what can we do about the polyatomics? What can we do about the polyatomics? Well, we're still asking that question. I think that now we have some prospect of being able to provide some answers, maybe not immediately, but certainly in the years to come. Okay, so that's roughly what I'm about. I'm going to sort of talk a little bit about molecules in astrophysics and the role that they play, at least give you some idea as to where they turn up and what they look like when they turn up. And then I'm going to talk a bit about the ExoMol project that was started by Jonathan Tennyson and Sergey Yurchencko in 2011, and my contribution to that by working on the carbon-3 molecule. And then finally, I'm going to say a little bit about the databases in which these data are deposited and opacities which are calculated with these data. Right, so molecules are pretty ubiquitous in astrophysics. They occur all over the place. And can I point to this? Ah, yes, okay. So you can, if you have, for example, you can imagine the existence of a large molecular cloud where you get some shielding from the stellar radiation field, be it near or far. And so molecules can form by various chemical reactions over a period of time to give you, in some simple cases, ethyl alcohol water, HCCN, HCN, HCl plus, and so on. And then these molecules can, of course, then form in denser clouds and condense to form stars, where more chemistry can occur in that process. And then the star and planet formation can proceed for a few million years, and eventually the star goes up the red giant branch probably and ejects a lot of material into the interstellar medium, or if it's a very massive star, it will become a supernova and return a lot of material, including molecular material, into the interstellar medium. That then comes back and works its way around the cycle again. And then so gradually, bit by bit, you're changing the chemistry of the interstellar medium as you go through one generation of stars to the next, and so on. Okay. So perhaps one of the greatest successes that Jonathan Tennyson's group had was to unequivocally and without any doubt establish the presence of water in sunspots. So we have a sunspot spectrum, observed sunspot spectrum, and previously to this 1997 paper, we were plotting here the wave number in inverse centimeters, for a very, very narrow range, running from 924.2 to 925.6, normalized to a continuum of roughly 1. Previously, that line was identified as a water line. That line was identified as an OH line. And this line was identified as another OH line. Then there was a silicon monoxide line there and another one there. And that was all that was identified in this particular spectrum. But Oleg Polyansky looked at this and he said, well, wait a minute, this is my water line list. So he was able to identify classify that line. I'm not going to go into all the quantum numbers that are listed here that identifies the line. That line there is another water line. That line there is another water line. That line there is another water line, and so on. 2 more over there, 1 more there. And that was, without any doubt, left you with pure knowledge that water exists in sunspots at a temperature as high as about 4,500 degrees Kelvin or thereabouts. Okay, so another example of the presence of molecules is the planetary nebula TTC1, and the full spectrum of it is running here from 5 microns to 30 microns to 35 microns. The flux positive Jansky's along here. is this spectrum here. The continuum, which is this dotted line, is due to silicon carbide dust. So if you remove that, then you're left with this spectrum over here, with these various emission features here. Now the red arrows are identified through a simulation as due to carbon-60, and the blue arrows are features which are identified due to carbon-70. And these are large buckyball molecules discovered in the mid-1980s. And the existence as to how to form is in itself an interesting problem. And presumably you have to start off with some carbon molecules, with carbon-2, carbon-3, carbon-4, and so on, gradually build, have a chain to build them up. But to the best of my knowledge, that isn't yet worked out. But on the other hand, there's absolutely no doubt that these molecules exist in the interstellar medium, and they're very stable because of that structure. I think of it in a two-dimensional ring. You've got benzene, which is a two-dimensional molecule, very stable. But extend that to 3 dimensions, go to carbon-60. It's a really stable molecule that exists there. Oops. Right. And so as Jorge mentioned, Carlos Lázaro and his collaborators obtained some spectra with the Carlos Sanchez telescope using their first version of the rating spectrometer in August 1983. And this spectrum here that I show you is a spectrum of HR 6765. And what we plot here is, oops. Yeah, right. Oh, one slide. Okay, so what we plot here is the wavelength in microns, going from 2.26 to 2.4 microns, and then the flux calibrated using Vega as the standard in ergs per square centimeter per second per micron, scaled on a scale of 10 to the minus 7. And so that the observed spectrum is the black line. And our various attempts to synthesize it are the beta lines. This here, there is the 2 to 0, and that is the 3 to 1, and that is the 4 to 2, and that is the 5 to 3 bands of carbon monoxide, where the carbon is carbon 12. Right? If you replace the carbon 12 with carbon 13, the 2 to 3 band, sorry, the 2 to 0 band moves here. So it moves from there to there. It weaker, of course, because the carbon 13 is not as abundant. And then the 4 to 2 carbon 13 band is here. So we were able with that to deduce in this giant the carbon abundance. And it's a metal porous star. So here we held the carbon 12 to carbon 13 ratio fixed at 10. Remember that the solar system value for the carbon 12 to carbon 13 ratio is about 90. We held that fixed at 10, and we varied the carbon abundance to go from about minus 0.25, minus 0.75, and minus 1.25. Logarithmically relative to the sun. Okay, and then those are these plotted lines here, and we reckoned we got the best fit with a value of about minus 0.75. Over here, we played the opposite game. We held the carbon to hydrogen ratio fixed, and we varied the carbon 13 to carbon 12 isotope ratio, and so we went from about minus 3, which gives you this strong feature here, to minus 30, to about minus 3, yes, sorry, it's a 3 rather than minus 3, and 30, which is a low carbon 13 balance there. And we reckon that the best value is a factor of 10 in the ratio of carbon 12 to carbon 13. So in other words, in this particular object, F4, carbon 13 is enhanced relative to the solar system by a factor of something like 10. That means you'll see geometric of So looking extremely doubtful. So do if I'm saying anything wrong, don't let me be waiting for this. Okay, so that being said, we now need to sort of think about just how much molecular data we actually need. And the answer is all of it, absolutely every single last time. So this is a spectrum published by Yurchencko, Tennyson, Bailey, and others, and received the National Academy of Science in 2014. It's a spectrum of a round world to 2M for 0.59 minus 14. And again, they're plotting the wavelengths from 1.4 microns to 2.2 microns. And the flux coverage of 0.21 on this scale here. The observed spectrum is the black line. Okay. If you take an incomplete like this, like the dark blue one, or the pale blue one, and for it to try and predict what the emergent flux would be, you've got something big problem here, and you've got a lot of problems down here. If you have the complete line, this it includes all lines of methane up to about so then you get a pretty good match to the data, and there's something like 50 billion lines. Yeah, and you see, if you don't hit the top to match the observed energy distribution, then you've got more structure for the answer for sure. Okay. So completeness is of essence. Accuracy is your transition is important also, just a second. But completeness is extremely important. So therefore, go to a lot of trouble to make sure the things works. Right. So highly explosive spectroscopy of exoplanets doing a transit. And the trick that has been devised here is you didn't wait for it to planet to a planet across a star and take highly explosive spectra very quickly already planet across the star and then to up here. However, what you really want then is an accurate blindness. If you do that, and we take this case of oops, if you do that, then let's take the case of methane, for example, and you make some assumptions about the rest frame velocity of the center of mass of the star planet system. And you make some assumptions about your speed. And you do your cross correlation for those range of assumptions. Then you will get and you measure the significance of any cross correlation peaks that you find. You find a nice maximum around here, which suggests you nicely the rest frame of the star planet system. And you've got an orbital speed for the planets of something like 120 to 130. And you can play the same game for another, with another molecule of water, and you get essentially the same result. So therefore, if you have a high quality like this, accurate wavelengths and densities, and cross correlate against the observed spectra, you get some useful information about the relative quality of the atmosphere. But you have to have boost like this with high quality and accurate okay, so the ExoMol project was designed to actually produce the data that was going to be referred to here. And this table here comes from the paper by Tennyson and Yurchencko collaborators published in the Journal of Quantitative Spectroscopy and Radiation Transfer in published in 2020. And in green, we've shown the molecules that are so far complete as far as calculating, getting high dispersion, high signal to noise, high quality data. So we can see there's a handful of molecules that we've done to that sort of standard order for each lead pass here, about 1 million micrometers solid. And there's another set which are coded blue, and these have, so shall we say, low dispersion data. That is where the line positions are not so accurately known. And those are all biochromatic activities like 2 and 4. And then there are other works that are in progress, the one that might be calculate, and others which are still to be in progress. Okay, so a new version of this paper is coming out this year with Jonathan tries to publish one every 4 years just to sort of keep the community abreast of progress. Right, so why carbon 3? Well, it's an interesting molecule. The fact that it was detected as long ago as 1881 from the spectrum of a comet by Huggins. And what Huggins, this is Huggins spectrum, I think, here. And what you can see here, the dark KH, the brown upper band, is due to carbon 2, and the T band, which is due to CH, if I remember correctly. Superimposed on, and then that is just reflected sunlight. Superimposed on that are these bright emission lines that you can see we can only originate from the comet itself. And Huggins said, well, I see similar spectra similar to that in play. And so it must be a carbon-based molecule. Exactly what he couldn't figure out. But I think for 1881, that's a remarkably nice spectrum, and that comes through in this paper. There we go. So they did a variety of experiments. First one concluded that it probably was CH2, but they eliminated that possibility by replacing hydrogen with helium in a lot of the experiments. And eventually it clinched it as carbon 3, because you see this band structure in which you've got 12, 12, 12, as you'll see before. But when you replace one of the carbon 12 atoms with the carbon 13 atom, then this band will be here, of course. And this band will be here. Okay, it splits into 6. And so then it's only good. And it appears in lots of places, sometimes about to find demonstrate. But anyway, on the basis of the what was known in the mid-1960s, Garcet and his collaborators did a band analysis of carbon 3. And it's essentially what you have here is a low-lying electronic band, which is X1 sigma plus G, and then another band, which is L1 pi U there. And all the comet lines are labeled here between these various levels within the electronic bands, which are essentially vibrational levels. So we use these quantum numbers here, going from the left-hand one represents the symmetric spectrum, and the middle one, which contains such asymmetric spectrum. And then you put a superscript on that to represent the L, which is the projection of the rotation quantum number of the vector axis. And then the left-hand quantum number there is the
So what we decided to do is suggest. So what we decided to do is to actually analyze all the low vibrational levels associated with this lower electron band here, confining ourselves to energies of less than 10,000 inverse centimeters. These are energies in inverse centimeters of here. So we're trying to compute complete blindness going up to 10,000 inverse centimeters. So in effect, that covers the one micron box. Okay, which is only puts the right. So interesting, carbon 3 even in the mid-1970s was such that Trevors and Gilbert made a laboratory measurement of its absorption cross section, positive here in emission, of course. Where they measure the cross section and express it here in inverse centimeters going from 1,400 to 2,200 and relative. And the observed is the plotted line here. And then they have some crude models that suggest that even at 3,000 degrees, this molecule exists and is prominent. And then they also observed an additional feature here, which they believe is 3 here. And then, of course, the peak actually shifts as the temperature changes. So that's the peak there corresponds to a temperature of 3,100. That peak there corresponds to a temperature of 2,000 degrees. And so that is the sort of thing that we have to try and do our calculations with their capability, or alternatively to demonstrate that with part of experiments and see correct. Carbon 3 is prevalent in the solar medium. Here we're looking at the spectrum. Here we're looking at a spectrum of a hot early type star, HD 169454, and we see the same carbon lines due to the same bands in the interstellar medium in the direction of this particular star. And so this is the observed spectrum here. That is a synthesized spectrum, and you can see the match is remarkably good. So it's quite prevalent in the interstellar medium, and in other places. So in other places, and we might have present in the interstellar before. The actual formation and destruction of carbon 3 was studied by Clegg and Lambert in their paper in 1982, and they sort of suggested, well, you can start off with something like C2H2, you can pick up an ionized carbon atom and lose the hydrogen to be with C3H+, and then that's going to go a variety of ways. You can either then just lose the H+, or by interaction with electrons be with C3, or you can lose both the carbon and the hydrogen in C2. So that was the main challenge that they worked out for the formation of carbon 3 in the interstellar medium. As far as I know, that is correct. So now, of course, I'm interested in these carbon big molecules, provided because of the interest in carbon molecules, therefore and so you see you can have carbon here, this sort of bond structure, a typical bond length of 1.2943 extrons, double carbon bond. The central carbon atom has all 4 bonds active. And then you can logically imagine how this might be extended to carbon 5, for example, carbon 2, 3, 4, 5, 6, 7, and so on. And then when you get up to more complicated structures, you start to form these bigger structures. And you can begin to imagine how these small carbon clusters might occasionally need to run on the ball. Right, so much for the observation. Now then, what about the method? We use ExoMol to calculate these data. So the methodology, as I've mentioned this diagram, is expected by Tennyson and Yurchencko, published in Astronomy and Geophysics. So you start with ab initio calculations. When we consider only the motion of molecules, motion of electrons for the moment, and using so-called Oppenheimer approximation, where you take momentarily the positions of the nuclei of the various atoms as fixed. And then from that you deduce what is called potential energy surface. And that is a surface which gives you the potential energy of the molecule for various wavelengths and various wavelengths. And so then you combine that with the kinetic energy to get the total energy to the tertiary wave. But in addition to that, you also need the dipole surface, and that too comes from the examination calculation. And then, having got the potential energy surface, you use a variation principle to actually take the motion of the atom. Okay, and so that then leads you to the Schrödinger equation, which includes now the motion of the nuclei, which you then solve, and that gives you 9 positions and 9 intensities. And that's it qualifies then as a molecular spectrum, for which you can get 9 lists of opacities. But of course, you also need to remember that we got in those cases, at least for some, molecular data written around. And so it's then you then go back and you compare your calculated positions with your line strengths with what has been measured in the lab, and that means that you can then feed that back into a refinement. You can then improve your potential energy surface, for example, and go around and do the calculation again, and then check against the law of nature again. You can keep going until you and the reason why this is important is certainly you want very accurate line positions for this sort of cross correlation. And it's still the case in most cases that you can get much more accurate line positions by measuring in the lab than you can by doing this sort of calculation, simply because the potential energy surface often needs to be desired. But a bit like in the case of water, for example, I think that Polyansky, if he would hear giving this talk, he would tell you that we can now calculate the potential energy surface for water to be better than the water. But I think that water is a very acceptable case. The water is what we do. Okay, so part of that requirement is what is called the model process. And what you do is you take all the laboratory observed transitions and see how they're all connected. And take all these, they're also represented in the case of carbon-3 by this diagram here. The blue ones are the lower electronic state, and the red ones are the upper electronic state, which we are not including in our calculation. And so you take all these sort of observed laboratory transitions, and then from that we infer the energies of the levels, of the low vibration levels in the model. Slide, yes, there we go. So I've taken this from the paper by Tennyson, published in 20th last year. And in this diagram, we're possibly the rotational quantum number from J to 0 to 60, and then the energy is the energies of the low vibrational levels in the lower electronic state, and those are the low vibrational energies, the low vibrational levels in the upper electronic state, the X1 signal plus, and the A1 pi. And as you would expect, a sort of a nice line trend here, which sort of enables you then to infer energies based on laboratory data, or if you like corrections to your energies based on laboratory data for a range of the projections of the rotational quantum number on the molecular axis, from level to 0 to and that in principle then we actually improve potential energy surface, actually improved line positions, and we found that we got very good at being and it's good up to about 10 inverse, 10,000 inverse, which is where we decided to start. The potential energy surface that we refined is the one by Schroeder and Sergey, published in 2016 in the Journal of Chemical Physics. And I've just taken this plot as an example of what potential energy surface looks like. Each of these particles here is in the line of 3 particles, going from the lowest potential energy here. The bond angle of 162 degrees is the bond angle that I've selected as because it's the equilibrium volume, and on the other two axes I of the variation of bond length running from about 1.2 to 1.4, which forms in R2, and similarly 1.2 to 1.4 in R2. Okay, so we've got two bonds on the bond angle. And it's a relatively smooth surface. The reason for making it false is you have to look for all calculations stuff, which are the consequence of the variable path back, things like that. And that can really put the mark in this book. They're there in the book. Okay, because it means that when you start calculating derivatives, have a lot of smooth surface. Your environment will always show in the derivatives. So how good is the simple Schroeder potential energy surface? Well, they published this diagram. They published this diagram where this is their experiment, and then they make a rough simulation using PT Silver, and you can see that it does a pretty good job over the range from 3,100 to 3,300 inverse centimeters. Well, these are the various vibration bands that they consider, which I'll show in the next slide. So, for example, we start here in the 0, 0, 0. So that's the symmetric stretch, asymmetric stretch, flex, and so that the time of transition is color coded. So here we're just increasing both the symmetric stretch and flex, and here we're increasing again the symmetric stretch and flex, so 3, and so on. And you seem to get very good at all the range of possibilities of flex anyway, and stretch as well over the range of interest. So that good. The program I use to do these calculations is Probe, which is published by Yurchencko in 2007, and it's a very nice program to use, but it's extremely expensive in terms of memory. Well, I set out from here, I put it on, well, 5 days all the time. You have to do the 12, 13 mix, which is complicated, because it's expensive. And that time that we have to decide how we would have that. But this diagram shows that you can, in principle, get very high accuracy. So what Sergey is doing here is he's comparing the accuracy that he gets compared with Johnson Tennyson's program DBR3P on a logarithmic scale, where the error is measured on base 10 logarithm relative to DBR3P. So a factor of 100 means that you're a factor of 2 to the factor of this is a 50% error here. It's going to be an error factor of 100. I said, yeah, factor of 100. That's right. And so if you want a very high accuracy, you've got to be very careful about the basis set that you represent the wave. And these are the positive dependent on the type of transition you're concerned with. And so these different bands, these different lines here represents different vibrational transitions. In the worst case scenario, even when you pick 22 basis points, you're only coming in around 50% accuracy. So we're doing our calculations with 56 basis points, and it was something that actually will be the agreement with the experiment is very good. Anyway, I think my first idea was to reproduce carbon 3 absorption. This is for the carbon 12, carbon 12, carbon 12. In the direction of the Sagittarius B2, the cloud. And this is the cloud which is separated from the galactic center of Sagittarius A. And Yurchencko and his collaborators have observed carbon 3 absorption in the direction of this cloud, and their data are the black lines. And my simulation with the two-cloud model is the red one. And so I'll just pick these three bands: the B2 band, the B2 line, the Q2, and the Q4 lines. I get quite a high space with a two-cloud model. The temperatures around 5 Kelvin, 10 Kelvin per temperature. So I was quite sure about that. The other thing you need to be careful about is the partition function. So if you look at this paper by Irwin, published in 1981, you'll find there some polynomial taking molecular and multiplied by the for a range of temperatures. In the case of carbon 3, those data are taken from an old piece of work by Lynas-Gray, if I remember correctly. Lynas-Gray, this right, I think this thing is also, nope, it's also. Yeah. So I plotted Irwin's polynomial fit here. As this red line there. Our data is the black line. And we're plotting here the partition function as expressed as a base 10 logarithm for temperatures between 1,000 and 6,000, 5,000 feet. And the difference here is an order of magnitude. But as far as our calculation goes, that is complete. We're not going to meet people that for any careful. And the reason I make that statement is that we find that it's when the rotational quantum number increases to 105, there are no more limits. We don't have rotational quantum number to include in the calculation. So provided we retain ourselves to lower the quantum time, we restrict ourselves to interviews within 10,000 versus less, then we're complete. And that can happen on the partition function is then complete. But almost independent of temperature, that's the difference there. Now the cross section, equally, ExoMol usually presents cross sections For temperatures of 300 degrees Kelvin, or temperature of 26 planets, and then the sort of hot temperatures of 2000 degrees Kelvin or thereabouts. And so our cross section here runs from a frequency of 0 to 10 to the 4 inverse centimeters. And we plot here base 10 over the cross section. Expressed in inverse square centimeter, running from -26 to -18. And again, you see we recover very nicely the peak here that Jefferson Gilbert observed in 1975. And again, you can see the sort of shift in the position of the peak depending upon the temperature. This other secondary peak down here is the low order billion book from 3 to 50 centimeters. And that that's what makes this molecule in a sense interesting, and why we can see it in absorption directly. Okay. Right. So Martin Nobel collaborators published towards the end of last year an experimental measurement of the cross section of carbon-3, and this is the energies that they considered, starting with the ground state here, the 0, 0, 0, and treating these levels here, consider all these various transitions up to the exciting electronic band, which is not included in our calculations. And so it was with some satisfaction that we were able to make a comparison between her experiment, which is this black line here, again running from about 1,900 inverse centimeters to 2,100 inverse centimeters, and this is her own simulation using PT Yoga, which is a rather more approximate method than we use, and our simulation here, which is what we calculated using the techniques I described. And we are very pleased to get that very good. And it's shown the same thing here, and get into more detail. The match to my way of thinking is remarkably good. You actually break that down with the top of the right, so nearly there. What we want out of this, of course, are databases. And data we can find the data and there is an ExoMol web page which will be databases. I'll just comment here a little bit on opacity databases, which are discussed by my legal collaborators. And what he did, and these 3 class 3 plots I'm going to show you, come from his paper published in 2022. And what he plots here is the base 10 logarithm of the Boston mean opacity per centimeter per gram, -6 to 0. And traditionally, what is used in astronomy calculations are the data occurrence. And you can see that in this case, and I'll explain what I mean by this case in just a second. The agreement with Ferguson is pretty good until you get down to low temperatures where Ferguson appears in deficit. And this is for the solar mixture. And this quantity R is a little bit of it. It was increased far by the one by so for having it is the density expressed in radical CC divided by the temperature expressed in data and expressed there as well. So if you take that, then all of our tend to like speed and correspond roughly to the time. So this is the same thing, but now R is changed to -3, so that would be corresponding to the theta. And now you can see the difference with Ferguson becomes a little bit more interesting. So you can see this inset here, the Ferguson is down by something like a factor of 2. And you have to remember that in all these modern calculations, so this is a lot of computation. So the difference will get more. And it's quite obvious. The comment that's made in these papers is that the difference is primarily due to the choice of the water like this that is included. So, for example, partial from Yurchencko, which is included in Ferguson, but then there are more modern water like this, like Lynas-Gray, which are published in 2018, which is the red line here. And also equally important, which I haven't put on the port, you can draw it, the line drawing. And that's another thought, but somebody else for the day. And finally, this plot here, which is perhaps where you get high density stars with sort of surface gravity is typical of an exoplanet. And then Ferguson, there appears to be a deficit by something approaching a factor of 5 or 6.
Questions? Nothing, yeah.
I thank you for the talk. I have two quite naive questions. One is about the experimental C3 spectrum. How do people get that? Get that in the laboratory, yeah. Yeah.
Well,
Okay. Okay. Another thing is, well, there's another database called Hytran, quite famous. Yeah. And so what's the pros and cons between ExoMol and Hytran?
First of all, we're talking typically about 5 billion lines per molecule.
5 billion per molecule. So Hytran would be much less. Mm-hmm. Okay. Yeah.
So there's some room to be
Thank you.
More questions in the room? There's, yeah.
So thanks, Tony, for a nice talk. And I think that I don't know anything, I must confess. So now I know a little bit more. So question is, you made a strong case for the need of this molecular data, but I got the impression, maybe I got it wrong, that the pace at which the field is evolving is not as fast as you would like, or something like that. Yeah. So my question is, which is more needed now? Is more, for instance, more labs, more observations to make progress on this? All of them.
Certain will help
Uh-huh.
all the work videos. But you have to remember what you do in the lab. The two way you do it is quite different. Everybody will have its part work on that. One more. So the first way up is to and use those to talk to your colleagues. Or my colleagues.
Yeah. Yeah, yes. I was expecting something like everything. Yeah. Thanks.
Thank you. Yeah.
Thanks for the very nice talk. One question regarding these opacities that are provided by the ExoMol. I guess they are computed assuming some equation of state. So is it equilibrium equation of state that you assume? Hmm. Yeah. Okay, and are there any of the rates, reaction rates provided by ExoMol for non-equilibrium chemistry computations? Okay, thank you very much. Perfect, thank you very much.
Anything else in the room? There is nothing online, so if no. So if nobody else has any question, we can thank Tony again, and thank you everyone.